Hello, I'm Rob Hirschfeld, CEO and co-founder of RackN, and this is a presentation about taming complexity, whether we should embrace it or eliminate it. And in this, we'll talk about why automation is so hard and what the challenges are of building really repeatable infrastructure. And I have a lot of experience doing exactly this. From my time at RackN, where we've helped customers create repeatable, globe-spanning infrastructure at scale, to my earliest days building clouds, data centers, and other types of infrastructure. In this case, I want to really drill in on complexity because we use complexity as a scare tactic. We look at things that are complex and we are afraid of them or troubled by them or concerned about them, and we really can't explain why. And I would encourage you to look at this reference material I'm going to talk about by Richard L. Cook about how complex systems fail. And in it, he makes many different points, but the first two are really important here. First, that complex systems are intrinsically hazardous, and thus it makes sense for us to be concerned when we see something that is complex and treat it with caution. And that's normal and reasonable. However, he also points out that complex systems are heavily and successfully defended against failure. And so I would ask you to think about the idea that it's not that we have complex systems and they're bad. Complex systems actually can be very well designed and function incredibly well and robustly. That is actually part of why we have the complexity. But we need to figure out how do we build complex systems that are heavily defended. And this is an important thing to understand. We're stuck with complexity, especially if you're on the infrastructure side. We see complexity all around us, and it's increasing. And we need to understand how do we take infrastructure as code and create a successful defense. And that is exactly what we're going to be walking through in the next 30 minutes. To do that, I want to start with a simple example, something that I accidentally stumbled into years ago when I was trying to bring 3D printing to a booth. I thought it would be wonderful to be able to print tchotchkes and handouts right there in the middle of the show floor. And it turned out that doing this was incredibly hard to do. The floor was not a stable environment. Getting prints working in a repeatable way, in a quick mode where we would have to run the system, was very hard, and frankly it was slow. Printing a plastic tchotchke is really good if I just need one of something, but when I'm actually trying to do it on demand and it takes 20 or 30 minutes to print something, it becomes really frustrating for everybody involved. And I bring this up because at exactly the same time that I was trying to do this printing experiment in our booth, we were also trying to do a very similar thing with clouds and shipping working clouds into customer environments. We would literally build a cloud in our lab, a minimal viable product for shipping one from the factory, and then send an engineer, who later became my co-founder, Greg Althouse, in an airplane at the same time the rack was arriving at our customer sites. And he would spend the time building that rack up. What we found is we could never actually deliver a rack with everything ready to go for the customer site. Either the software was changed between the time we shipped it and it was installed, customer requirements shifted, or what they thought they knew they didn't. We always found ourselves rebuilding the infrastructure on site. And we built automation. What Digital Rebar and what RackN does today is actually an outcome of how do we build infrastructure dynamically. But the problem here was not that we had to build it on site. We solved that problem. The challenge here is that every time we did it, it created a different deliverable. So none of our customers could actually reuse the automation that we had built on a previous customer. And if we fixed something, we couldn't take it back to our previous customers and improve their automation. We literally were doing things one at a time, automated, but one at a time. Exactly like what happens with a 3D printer, where I can have all the CAD drawings and recipes to print a machine, print a part, but fundamentally, I'm doing it one at a time. Each one is unique. And this is a challenge that we face across the industry. We have to recognize that while we have great tools, Terraforms and Ansibles, while we have great people that really know how to do their jobs, and we have great vendors that have incredible platforms, none of this actually works together well. We keep reinventing everything that we're doing. Even when we're using standard parts and components or standard tools or standard training where people have similar experience, we keep building things that are patched together. If you will, think about it this way. If I was building a house and in the bedroom I was using European plugs, and in my living areas I was using US plugs, and in the kitchen I was just wiring things together with wire nuts and making it up as I went along, we would end up with a complete mess. Our building codes would not actually allow us to do that type of system, and we do this in IT all along. And then we put up the drywall, we get a log from JBug, and we smell smoke behind the walls, and we don't know where to look. That's where we are today. We need to have consistent, repeatable processes that we're able to use team to team to team within the same organization. And even better, we want organizations to be sharing and reusing each other's components across the board. So let's talk about how to do that, because fundamentally our complexity story in creating a defensible system is all about how we actually make this work. So let's go back to our 3D printing model. The analog for 3D printing as a 3D printer is injection molding. Fundamentally, 3D printing and injection molding are the exact same thing. They both will take a plastic, heat it, and then form it into a shape. The way they do that is dramatically different. In the 3D printer, we're actually heating that plastic and then moving the location of that print underneath the head, or we're moving the head to deposit the plastic in exactly the right spot, literally building dot by dot as we go. An injection molding machine, if you're not familiar with the technology, heats the plastic up. It takes a mold that has the shape of what we want, and then it injects the plastic fluid across the mold, and then it fills all the cavities in the mold, and then sets that shape. And so it's incredibly reliable to inject plastic, shape, form the mold, and then get the next piece. You can even build multiple pieces at the same time. So how are these different? If they're both building plastic parts, they have so much commonality. Why are they different? Well, they're different because the use cases are remarkably different. A 3D printer is amazingly powerful when you need a part that is going to change a lot. It has incredibly low setup cost, has very low setup effort once you've gotten that one part. But once you start building parts, it becomes incredibly expensive per part, and it's not very reliable. It's sort of low tolerance, hard to make quickly. Injection molding machines are the exact opposite. It costs a lot to build a mold, it costs a lot to build the machine, so there's a high setup and system cost. But once you've paid that price, you can stamp out parts at basically the cost of the plastic. And at that point, you have highly reliable, very fast, repeatable results at low cost. And it's important to understand, as we look at systems, that there are times when you want both. Fundamentally, the 3D printing is great for this experimental learning phase where we want fast design iterations and one-off components. But it's not very reusable. Even if I was to give you my print file, you would end up tuning and tweaking it and making it work just for you. It would be very hard for you to share that back into my systems. The injection molding machines are just the opposite. You can take a mold and use it in just about any machine. The molds are incredibly portable and easily reused. They're great for high volume and reusable components. But once you've set that mold, it's incredibly difficult to make changes to it. You better know that you've gotten it right by the time you build that mold, or you're going to be going back to the machine shop and doing another expensive mold. So there are times when you want fast experiments, and there's times when you want long-term stable. Both are important. And when you think about this in an infrastructure as code framework, what we're really saying is that we want to do our development where it's fast and iterative, and we're doing small sample sizes. But once we get to operations is the opposite. We want that automation to run reliably over and over and over again. We don't want to have to think about it. We want it to just work and be cheap and fast and reliable. And so the best system that we can think of here actually blends capabilities of the 3D printer with capabilities of the injection molding machine. So when we look at this, what we're really thinking about doing here is not just doing injection molding for one part, but actually building an infrastructure pipeline of scalable and reusable components, literally connecting together injection molding operations into a series of components, because our systems are not just made out of one thing, they're actually made out of chained components. And then, of course, what we want to be able to do is take that pipeline and adapt it to diverse requirements. So we want to have our pipelines be able to make decisions or adapt or change or be able to switch one cloud provider for another, one hardware provider for another. That's a normal expected consequence of this. What we don't want to do is beware of false standardization. We don't get to say that we have done it well for one team, one department, one operation, and then handed it off to another team. That's a local optima, and that's not a system. It's a whole bunch of locally optimized solutions and is not actually a pipeline. If you want, we can be specific about what that looks like probably in your organization, where we have one team using GitLab, another doing Terraform, another doing Ansible, and another doing Kubernetes. And even though they're all connected together eventually in infrastructure, they're all managed completely separately. And so we've got teams that are doing this work, but then handing it off between each of them, which is really not repeatable. It's not effective as a pipeline. You can think, oh, that's not me. We don't have manual handoffs. I've written scripts that enable me to do this. And I'm sorry, but gluing to get things together with custom scripts is only marginally better. You now have custom solutions for that, in which you have tribal knowledge embedded into these systems, connecting them together. And that's only marginally better. In some cases, it's actually worse, because any changes to this pipeline, and you're going to be finding your script failing. And that is not a place that's actually breaking the standardization and the reliability. It would be like in an injection molding system, if your molds weren't right, and then instead of updating the molds, you just hired somebody to sit next to the machine and trim the part, or glue in a wire or something like that, or an extra widget to make it work. And that happens all the time in manufacturing lines. If you look at your circuit boards, you'll see wires soldered into them to solve problems that were too expensive to fix. So it does happen, but we want to get away from this model. Instead, we want to actually build an infrastructure pipeline from scalable and reusable components. So that means that we have to be able to take all of these standard operations, our injection molding machines, and then hook them together with conveyor belts, so work flows smoothly through the system from a processing operation to another processing operation. If you want to think about this in pipelining terms, it helps to understand that the injection molding here is the automation component, the Terraform, Ansible, Kubernetes, and the conveyor belt is our shared data, our integrations that glue things together. And it's important to recognize what we're talking about here is not just automation tools that work in a vacuum. It's actually a system that connects all these pieces together. And that's why it's really important here to look at it as a system. Reusable components put together with an integration layer that builds a system. But is this defensible? We have created a system, we've gone through and eliminated complexity by having highly repeatable components, but what does it take to actually make this defensible against complexity? Because we can have a system that is way too rigid and hard to change, and that causes us to have to work around it. What we still need is a way to inject and extend with new specialized behaviors, because we're looking for a resilient complex system, one that is able to adapt and change and build defense mechanisms into it. So what we're really thinking about here is not just, can I build a factory that has standardized equipment with a conveyor belt between it, but how do I make it so that I can adapt and change as my systems change, as I get upgrades and patches. The idea here is that we want to be able to mix in the benefits of 3D printing, the fast iterative design, where we can still automate and create a repeatable result inside of this pipeline. So the pipeline has to be extendable to include custom parts, custom operations, without breaking the flow of the overall pipeline. Because what we really want to see, and what infrastructure as code fundamentally means, is that bespoke 3D printing automation becomes standardized automation. It actually moves back into our process. when that happens, we have repeatable components. We've reduced the complexity of the system over time because more and more components are standardized and fit together in a predictable way. And then that reduces the cost of our overall system over time. We're able to move automation through the systems quickly and still been able to respond and adapt. The challenge, what happens otherwise, if we make it too easy to bypass the system, we're really just collecting unreliable components together and hoping that things work. And ultimately, we start bypassing all of the standard things because they don't work exactly right, and we just keep putting together more and more 3D printers. This, to me, is where we are today. We've got a whole bunch of tools that do individual things. They are pretty reliable. They're definitely automatable, but they, as a system, aren't reliable enough. And what you'll see here is where we actually end up invoking the third item in Richard Hook's list. We're actually saying catastrophe requires multiple failures, so that single point of failures are not enough. This is why when we hook things together, if we have unreliable printers, if we have printers that need a lot of adjustment and care and maintenance, then that little bit of care and maintenance is going to spread throughout the system and more likely to cause the entire system to break, which is going to put us back into manual failures or into one team writing their pipeline, but no other team being able to use it. And this is really a dangerous thing as we build more and more automated systems. And it's why we've had so much trouble creating shared automation. We've ended up looking at these systems as having very inconsistent results. And my risk of bringing in somebody else's code is much higher if I can't reliably run my system over time. I don't want to bring in or change it. We end up with systems that have automation but don't have portable or shareable automation, or don't have reliable and robust automation. And we see this all the time. We have automation that has inconsistent results, that has increased complexity over time, and increased cost over time. So I've seen this many times in my career. We get a system that's automated, it's working great, and then over time, the automation we've built decays, and might decay very rapidly, to the point where we go back to not being able to use it and share it. If you think about the example I gave from my early days at Dell, what would happen is we would have to create 3D printed automation in every rack we installed. And when we did that, we weren't able to go back and fix it in other sites because we didn't have the reliable pipeline that would let us take the code and press it through a mold over and over and over again. That lack really caused us a lot of pain and suffering, and ultimately made us just not even try to share automation code. And that fundamentally is the goal. It is incredibly important for our automation and platform teams to support infrastructure as code chaining and reuse, because we really don't have time for us to keep reinventing the automation and building a pipeline from scratch over and over and over again, team by team by team. It's just a waste of effort, but it's more than a waste of effort. It's actually a security risk, a standardization, a compliance problem. There's a lot of times where capabilities and features of the systems are not used because people don't have time to do the automation that another team might have gotten working. And then when it comes time to drive that process faster, we start to expose bugs and issues. So we really look at this as a challenge of building a reliable infrastructure pipeline where you can use the same modules, the same injection molding machines, and the same molds on every customer in on-prem, edge, or cloud, so every environment, and on day 0, day 1, or day n. So the same things that we use to build and set up can actually be used to patch, update, and maintain. This idea of an incredibly reusable automation system, not just the tool that runs the automation, but the automation itself being reused and shareable, is transformative in how things work. It allows the same site, the multiple sites to have the same automation, different teams to share automation and work together and collaborate. It allows different companies to actually get the reuse and reduce toil across the industry. Because frankly, nobody needs a new boot provisioner or OS installer or a multi-cloud integration system. What they really need is to focus on the layers above that and just drive that work through the pipeline. Add the 3D printing when they need it, and then keep going. And this is what it looks like for RackN when we help our customers do this. We are able to go through and, working from infrastructure as code, look at a system where we can do provisioning then pipeline to configuring, then pipeline to operating, then incorporate systems into a cluster and coordinate the operations, and then finally orchestrate all that together so that you have ongoing response in the system. That ongoing cycle where every time we improve the components in here, we actually are able to feed that back into the system is absolutely essential to us being able to create reusable automation. And you have to have this type of infrastructure around your automation, or it's not possible to create the sharing. Both are necessary. The injection molding machine and the mold are meant to be set together. And then the way you connect those pieces together, your conveyor belt for automation, is also important. They all connect together. I hope this has been helpful. We're really thinking about not just how you automate things, but how you collaborate around that automation. How do you make it reusable and portable so that as you're building a hyperscale or a distributed infrastructure or distributed teams, they're able to collaborate and work together. You have consistent results across all your organizational efforts. And that is what Infrastructure as Code is about. If you're interested in hearing more about this, please visit RackN.com. We would love to talk to you about how you can create the type of robust, resilient infrastructure as code systems that scale both across your organization in terms of sites, clouds, and most importantly, your different teams. Thanks a lot, and I'll see you later.